Hey guys, hope everybody's doing okay. What we're going to do today is move on to our second law of thermodynamics, which has to do with entropy and spontaneity. So I'm going to define spontaneity first, and then we'll define entropy. Then we'll see how those two things are related in terms of a reaction or a process that may or may not occur. So how do we know if a reaction will occur spontaneously or not? Spontaneity is something that proceeds on its own without any outside assistance. The newer vocab that the College Board is more prone to using is thermodynamically favorable. So usually I'll say a reaction is either spontaneous or non-spontaneous, just to keep it simple. But you could substitute in thermodynamically favorable in for spontaneity, or not thermodynamically favorable for something that is non-spontaneous. So I'll try to use some of the newer vocab a little bit more than the word spontaneous or non-spontaneous. But what I'll try to use, like I said here, is thermodynamically favorable in place of spontaneity. Okay? There are various forces that drive a chemical reaction or a chemical change. The first law of thermodynamics has to do with enthalpy, which is delta H, and that's energy. Okay? So a change tends to occur so that the enthalpy of your final product is less than the enthalpy of your reactants. So we're going to look at these potential energy curves a little bit more in actually the kinetics unit that we do. But if you look at the screen here, our potential energy is on the left-hand side. It's stored chemical energy in the bonds of the substance or substances that are involved in our reaction. And we have our products over here on the right. You can see that there's been a loss or a release of energy here. Okay? That's a thermodynamically favorable process, is having a product or products with less energy than your reactants. Okay, so a curve like this is definitely an exothermic reaction, because exothermic reactions involve a release of energy. So that's really, really important here. However, this can't be the only driving force behind reactions, because not all spontaneous reactions are exothermic. There are lots of endothermic reactions that are very spontaneous. Okay. And on the slide there it says, can you think of a spontaneous reaction that's endothermic? One of them that's very common that we've talked about a lot is the melting of ice. So if you have an ice cube and you leave it on the counter in your kitchen, it's going to melt. But that's definitely an endothermic process. Okay, the energy is going into the ice cube, and the particles start to move faster, right? And the ice starts to melt. So that's an example of an endothermic reaction that is thermodynamically favorable. It is spontaneous, but it's endothermic. So there has to be something else driving a chemical change. If it was just enthalpy, if it was just delta H, then the melting of ice would not be spontaneous. Okay, but it is. So what else is involved here in terms of driving forces behind a chemical reaction? The other term here, or the other factor that's involved, is entropy. All right, so enthalpy is energy. And that is your delta H. So we make sure we know what these are. And entropy is our new term for today, and that is a delta S. All right. Students sometimes get these confused because they are very similarly like spelled and all that. Enthalpy has the letter H in it. So students sometimes think of enthalpy, oh, there's the letter H, must stand for heat, or delta H. And entropy doesn't have that. All right. So that's one way to remember it if you're struggling. So again, what's it mean to be spontaneous? We have our reaction here, A plus B yields AB, and we have our reaction car, all right? And the reaction is going to proceed to the products, like naturally, okay? Spontaneous or thermodynamically favorable reaction. So there's no extra help here with this. It's without any external forces, okay? Examples of this are rusting. So you can see an example of that on the slide here. That's a spontaneous process. Same thing with our Bunsen burner. Now I know we need to add a little bit of activation energy to light the Bunsen burner with our striker, but once we do that, the reaction just goes. It's going to go until we run out of our methane gas or our oxygen gas, right? If we run out of one of our reactants, the reaction will stop. But otherwise, this is going without any external forces other than a little bit of activation energy to get started. So what we need to understand here is that substances desire stability. Okay, so for enthalpy, that stability is a lower energy state. Okay, so on the left-hand side of our potential energy curve here, we have a higher energy or enthalpy, which is generally less stable. And you can see that since energy is on the y-axis, we are losing energy. Okay, we'll recognize what this is a little bit later. That's an activation energy to kind of get that reaction started. And here again, here's our reaction car. Exothermic reactions will be spontaneous or thermodynamically favorable because we end at a lower energy, which is a more stable enthalpy product. Okay, so here's our example with ice melting here. And the question on the slide says, so only exothermic reactions are spontaneous? We know that the answer to that is no, right? Ice melting is an endothermic process. Look at where we started. Here are the reactants. Here are the products. And we're starting with some amount of energy. And our reaction is gaining energy. So we're ending at a higher energy state than where we started. And that makes sense. Ice is a solid. It doesn't have a great deal of energy, right? With particle movement, if you think of how the particles move in ice. And then as it melts and turns into a liquid, those particles have much more energy, right? They're moving a lot faster. So we do have a gain of energy, an input of energy into that system, which is an endothermic process. So that means if an endothermic reaction like this, like ice melting, is still thermodynamically favorable and spontaneous, enthalpy can't be the only factor involved in why ice melts. So we're going to look at entropy today, all right, and look at how does that relate to spontaneity. You have to look at both of these factors, together here to determine if a reaction will be spontaneous. You can't just look at enthalpy and determine if it's spontaneous or not. You can't just look at entropy on its own and determine if a reaction is spontaneous or not. It has to be a combined effort between the two of them. So the delta S, or the change in entropy of the universe, is greater than 0. All right. So what is that? You can see the image on the screen here. We have a highly ordered substance, right? And we're going to have an increase in entropy, and we're going to create a more disordered substance. So entropy really is defined as the amount of disorder that a substance has. All right. So the higher the disorder, the higher the entropy is going to be. All right. So the disorder or organization of a system is entropy, and we're looking for a more disordered, like chaotic system. All right. So I mean, even looking at it visually here, the picture on your screen, towards the right, the more spread apart is the more disorganized. That is the more favorable, I guess, product here, okay, than the highly ordered substance on the left. So the universe prefers disorder. Okay, we could see that all around us, right? So I have a little clip here to show you how the universe prefers disorder. And it's a video of a couple years ago. My son Aiden and I built a really big cup tower, like a plastic cup tower in our basement. And of course, that can't last more than like 1 minute in its fully functional standing form. So this video is a great example of how the universe prefers disorder. So let's watch that real quick, and then we'll move on and do a little bit more of this. Okay, buddy, you ready? Go ahead. Let's do it. Oh boy. Okay. What I try to tell students here when I talk about the second law of thermodynamics and entropy is to embrace the chaos. All right. So I'm a perfect example of this. This is a picture of a couple years ago. My kids were a little bit younger. I mean, my living room is still a mess, okay? But here's just, I took a picture of the second floor, from the second floor of my house down to the living room. We have a little balcony that like kind of overhangs. And you can see it's a total wreck. So no matter how many times I take all these toys and organize them, okay, and put them where they go, as soon as my kids get down there and start playing, chaos erupts, right? So the universe prefers disorder. So this is the preferred state of my living room, okay? Because no matter how much I organize it, it always ends up like this, or worse. Okay, so use this to your advantage. All right, so if your parents are giving you a hard time about your room being a mess, or the living room, or you didn't clean up after yourself when you're in the kitchen or whatever, like, listen, guys, like this is the second law of thermodynamics. This is an increase in entropy. This is the preferred state of my room. This is the preferred state of our kitchen, and they really can't give you a hard time about it because you're just following the second law of thermodynamics, which we're learning about right now. So, the entropy of the universe is always increasing. Okay, so we're always increasing the amount of disorder in the universe. And you can see that there's an example of that here on the bottom of the screen, and it matches up with your note sheet. We have a vessel on the left where you have a gas substance, and then there's a stopper here in the middle. Okay, the stopper is pulled, and after some amount of time, the gas, moves over into that vessel on the right. Or some of it does. So we have gas on the left and on the right in both parts of that vessel with the opening here, with the stopper removed. And on the right-hand side, it says, what's the probability it will on its own, okay, that's important, on its own look like this? Well, there's basically no probability at all. So here we are on the left, we are more ordered, all right? And here we are more disordered, all right? That's the preferred state, okay? That's the preferred state of this setup here once I remove that stopper from the middle. This is, again, more ordered on the right. It's not going to do that on its own because the universe prefers disorder and an increase in entropy. So it says rank the following from highest entropy to lowest. So our entropy value, we can look these up. It's a delta S value. The larger it is and the more positive it is, the more disorder there is. Okay, we'll talk more about that a little bit later. But we have ice, water, and steam. Rank the following from the highest entropy, so the most disorder, to the lowest entropy, the lowest amount of disorder. Well, the greatest amount of entropy, the greatest amount of disorder is definitely going to be steam. Okay, so this is 1. Water would be 2. Ice would be 3. All right, so you can take a look at the picture here of the particle diagram. It's not necessarily in the right, they're not matching up with the picture behind it. You can see the ice in the more orderly form, liquid water, a little bit more disorder, particles freely flowing around one another, and the water vapor in the gas state, particles are more and more and more spread apart and more disorderly. So the conclusion here we need to have is that solid substances have the lowest entropy or disorder, and gaseous substances have the highest entropy or highest disorder. Okay, let's take a look at a couple other examples. We have a solid table salt sample on the left, says NaCl solid over here. And here we have an aqueous solution of salt, NaCl aqueous. So which one has the highest entropy? That's your particle diagram of your table salt. It's our lattice structure, right? And here it is when it's dissolved. So if you just look at that visually, it's very easy to see which one has the greatest amount of disorder. The one on the right, the table salt, the aqueous solution of table salt, is definitely more disorderly and has a greater entropy value. So dissolved substances are more spread out, the particles are, so therefore they have a higher entropy value. Really easy. Next one, you have 50 degrees Celsius water and 20 degrees Celsius water. And if you look at the particle diagram for this, you know that hot water is going to have greater energy and the particles are moving faster, okay? Cold water, the particles have less energy, so they're moving slower. So a substance at a higher temperature has a greater amount of disorder or chaos, right? Because the particles are moving around over one another faster and they're generally less organized. With the cold water, they're moving slower. They're a little bit more organized because of that slow movement and the less energy that they have. So our conclusion here is that substances at higher temperatures are more spread out and therefore they have a higher entropy value. Last one, when we look at moles of particles, this one can be a little confusing. So which has the highest entropy? We have 2NH3 yields 2H2 plus N2. So there's a couple ways to look at this. The first conclusion we could come to is the more complex molecule has more disorganization. Therefore, they have more entropy. So that's the first thing you can look at here when you're looking at NH3 and then H2 plus N2. Something else you could look at though, and that conclusion might bring you to believe that the NH3 has a higher entropy value because there's more bonds there. It's a more complex molecule. But one of the rules I tend to go off of when you look at a chemical reaction is actually conclusion number 2. And conclusion number 2 says the side of the reaction equation with the more total moles is more spread out. And these are gases, right? So all of these are gases here. So this is especially true. Okay. Therefore, it has more entropy. All right. So we have 4 moles of gas on the product side. We have 2 moles of gas on the reactant side. So I would tend to say here that the 3H2 plus N2, if you look at the balanced equation here, that is going to be more disordered, okay, and have a higher entropy value than the 2 NH3, the 2 moles of NH3 on the reactant side. All right. Generally, if you look at your chemical reaction, if you have gases on one side and solids or liquids on the other, again, going back to one of our previous examples on states of matter, entropy, the higher entropy value is going to favor the side of the reaction with more moles of gas particles than solids or liquids. All right, guys, let's take a look here at how all this comes together to determine if a reaction will be spontaneous or not. So remember, we have 2 forces that are driving a chemical change or chemical reaction. One is enthalpy, and the favorable enthalpy value will be exothermic. Okay, so exothermic reactions are definitely favorable for driving a chemical reaction. And we have entropy, which is what we just looked at. And for entropy, we want very large positive entropy values. So that's where reactions are increasing in their disorder, and therefore the entropy value is increasing. So both of those, exothermic reactions for enthalpy and greatly disordered reactions for entropy will drive the reaction forward in a favorable direction, thermodynamic favorability. So let's take a look at a couple scenarios here and see if the reaction will be spontaneous or not. Let's see if it will be thermodynamically favorable or not. So we have an exothermic reaction where entropy is increasing. So here's our reaction vehicle, right? We want it to move in the forward direction, okay? We want it to be spontaneous or thermodynamically favorable. Let's see if that's going to happen. So we have an exothermic reaction. So that's favorable in terms of our enthalpy. And we have a reaction where the entropy is increasing. That is also favorable. Okay, we just went over that. So we want exothermic reactions. We want an increase in entropy for reactions. Both of those things are occurring here. So the reaction is going to move forward. So on your note sheet, that is a spontaneous reaction when we have exothermic and an increase in entropy. Okay, so that's good. Let's take a look at another scenario where we have an endothermic reaction and a decrease in entropy. So endothermic reaction is not favorable for enthalpy, but doesn't mean the reaction won't be spontaneous, because let's look at what the entropy is doing. All right, so that the enthalpy is working against us here. We have a decrease in entropy. So we have a decrease in disorder, which means we're having a more orderly reaction here. That's not favorable either, okay? So the delta H, your enthalpy is working against us. The delta S, your entropy, is working against us here. So there's no way to push this reaction forward in a spontaneous manner, right? So this type of reaction will never be spontaneous. So if you have an endothermic reaction and a decrease in disorder or a decrease in entropy, that reaction will never be spontaneous. A couple other scenarios here. We have an exothermic reaction where entropy decreases. Let's see what happens here. Exothermic is favorable. That's going to push our reaction forward. But a decrease in entropy is not favorable. So look what happens. You have enthalpy working working for us for spontaneity. You have entropy working against us, right? So what's going to happen here? Well, it depends. It depends on how exothermic is this reaction and how much does the entropy decrease? How much does our disorder decrease? The size of those and the temperature the reaction occurs at is what's going to determine if this is spontaneous or not. So this is actually the next lesson that we look at, and we actually figure out when we have something like this, is it spontaneous or not? We have to look at we have to look at some other variables here. So the answer to this for now is maybe. It might be spontaneous, it may not be. Last one. You have an endothermic reaction where entropy increases. So endothermic reaction works against spontaneity, okay, because we want it to be exothermic. And an increase in entropy is good. That's working for us. So we basically have the same situation as last time, except switched. So in this case, entropy or disorder is working for us in terms of spontaneity. And then enthalpy or heat is working against us in terms of spontaneity. So again, it's going to boil down to the temperature here and what that is, and the magnitude of your entropy and enthalpy. So we have to look at those all together as a whole to make a more to make a better prediction here for whether this will be spontaneous or not. So for now, it's a maybe. We have to look at more information in future lessons. Okay, that takes care of it. So that's our second law of thermodynamics. Overall, I don't think it's too difficult. We want to look at, is the disorder of your system increasing or decreasing? That's what entropy is. And then we want to start putting things together here. And all of our laws of thermodynamics all work together. So we want to combine our enthalpy, which is our first law of thermodynamics, our heat or our energy. We want to combine that and relate it to our second law of thermodynamics, which is our spontaneity or our entropy, our delta S. And then we're going to see how it all comes together in a little bit. All right, guys? Thanks.